Welcome to the Foundry by Forge College. It's so great to have you back. If you're joining us for this module in the Advanced Solana Concepts track, well, you are definitely in the right place to seriously level up your engineering skills. Today, we're jumping into a topic that really separates the beginners from the absolute pros: observability and Sealevel performance signals. This explainer is basically going to give you X-ray vision. You'll finally see exactly what's going on under the hood of your programs. Because, let's be honest, we've all been there, right? In the last lesson, we went through the Sealevel environment setup and tooling, and you successfully got Sealevel running locally. Awesome. But then you fire off a transaction, and boom, it fails. You're just sitting there staring at this massive, intimidating wall of terminal text, wondering what on earth just happened. It kind of feels like trying to read the Matrix without any training. But don't worry, that wall of text, it's actually trying to help you. Okay, let's dive into this. Here is our engineering blueprint for today. We'll hit decoding runtime signals, mapping signals to stages, the sorting center model, some troubleshooting examples, the waterline checklist, and finally, next steps. All right, starting right off with section 1, decoding runtime signals. Basically, understanding your outputs. So the core challenge here is moving from all that raw, overwhelming noise to actual, actionable hypotheses. Luckily, Sealevel emits 4 distinct classes of signals to help us out. First up, we've got textual execution logs. These are your standard program logs and runtime diagnostic lines. Second are structured trace points. Honestly, these are just breadcrumbs you intentionally leave for yourself so you don't get completely lost in the dark woods of your own program's execution. Third, we have counters and metrics. These give you numeric aggregates so you can spot trends over time. And finally, end-to-end timings, which measure the whole shebang from submission all the way to confirmation.
Moving on to section 2, mapping signals to stages. This is all about making those lifecycle connections.
Now, what's really interesting here is that knowing what the signals are is really only half the battle. We need to understand exactly where in the transaction lifecycle they actually appear. Connecting a specific log line to its exact execution stage, that instantly narrows down your problem. If you see an account lock trace, bam, you know immediately you're stuck in the account locking stage. It's a contention hotspot. See compute exhaustion, you're stuck in program execution. CPI traces naturally point across program invocation issues, like maybe excessive nesting. By just asking yourself, wait, which lifecycle stage produced this signal, you stop yourself from chasing totally irrelevant noise. Which brings us to section 3, the sorting center model. Let's build a mental framework for this. To make all of this abstract stuff feel a bit more, physical, let's introduce an analogy. Welcome to the sorting center. I want you to imagine that your transactions are packages, the accounts they interact with are storage bins, and the CPU cores executing them are your workers. Now, if too many packages are all trying to be stuffed into the exact same bin at the same time, your workers queue up and throughput just plummets. On the flip side, if a single package requires an incredibly deep, complex inspection, well, it eats up all of that worker's compute time and delays everything else. Let's put this into practice with section 4, troubleshooting examples. Time to fix some traffic jams. So what actually happens when our sorting center experiences a massive traffic jam? Imagine you're running a local test suite. You're firing, say, 100 transactions per second, and all of them are targeting a very small set of escrow accounts. Everything starts fine, but after a brief warm-up, things start failing intermittently. Out of nowhere, your throughput just falls right off a cliff. You open your logs and you see this: trace, account_log, contention, account, retries equals 3. Using our sorting center analogy, this specific trace means your workers are literally fighting over the exact same storage bin. They're just standing around waiting in line. Now, the fix here isn't to go in and aggressively optimize your program's compute usage. Nope, the fix is to shard the accounts. You literally just need more bins so the workers can work in parallel. So the absolutely crucial point here is recognizing the difference between a locking traffic jam and compute budget exhaustion. Account contention, that means you've got many packages fighting for one bin. Compute exhaustion means a single worker simply took way too long inspecting one highly complex package. They require completely different solutions, and the beauty is your logs tell you exactly which one you're dealing with. And then there's the absolute terror of hidden CPI expansion. Imagine deploying what you think is a perfectly efficient transaction, only to realize a silly typo in a helper program caused a recursive loop. Next thing you know, you've got 50 nested cross-program invocations, and your compute usage just explodes. But again, if you check your CPI traces, you'll see exactly where the nesting loop's out of control. You can isolate it and fix that rogue code path right away. All right, section 5, the waterline checklist. Let's talk about prioritizing your checks. To help you prioritize exactly what to look at first when things inevitably go wrong, we use a second mental model. We call this the waterline. When a problem occurs, the visible surface level symptom is always the same: bad end-to-end latency. Things are just slow. But the root causes, those are submerged. And this brilliantly illustrates how you should approach debugging. You should always check the shallowest, easiest to detect issues first before diving into some complex profiling deep dive. Account locking, that's a shallow issue. Compute limits are deeper. And scheduler saturation, that's at the very bottom. This actually gives us a definitive, step-by-step diagnostic manual for your local Sealevel runs. Step 1, try to reproduce the symptom locally. Step 2, check for account locks. Remember, that's the shallowest issue. Step 3, check your compute limits. Step 4, check CPI traces for any of that unexpected nesting we talked about. And Step 5, confirm your findings with high-level metrics. Following this workflow forces you to validate your hypotheses quickly and cheaply. No more wasting hours on deep dives you didn't even need to do. But, sometimes you just can't reproduce a bug locally. It happens. That's when you turn to a latency histogram. If your histogram shows a heavy tail distribution, meaning a small chunk of transactions are taking exceptionally long to process, it usually points to resource saturation. Think CPU bottlenecking or account contention, rather than a deterministic bug in your code. It's basically a giant neon sign telling you to look at system resources instead of digging through line-by-line logic. Finally, Section 6, Next Steps, Gearing Up for Parallel Execution. We've definitely covered a lot of ground decoding these performance signals today. Let's move on and see how this builds perfectly into our next topic in the track: Introduction to Parallel Transaction Processing. The really incredible thing here is that these exact same signals, traces, and metrics you literally just learned to read, they're going to map directly to scheduler decisions and transaction interleaving in the next lesson. Your ability to read these runtime outputs is going to make everything going forward incredibly concrete. So I want to leave you with a bit of a challenge. What is the absolute fastest confirmation test you can run locally right now? Seriously, I highly encourage you to spin up your local environment, run a small workload that intentionally causes account contention, and use the waterline checklist to diagnose it. Get your hands dirty and put these skills into practice. If you want to dive deeper into this subject or explore a massive library of other Web3 educational resources, be sure to visit forge.college. Keep building, keep exploring those logs, and I will see you in the next explainer.